Oops. Okay, so continuing on here, let's see. So we've got the, let's talk about the mean, okay? And I think many of us are familiar with the mean. Symbolically, the symbol we use is x bar, okay? And the way we calculate the mean is we add up all of the numbers, all the values, and divide by how many we have. Or we call that the sample size. Okay? Or symbolically, we would write x bar is equal to the sum of the x values, so adding up all the values, and we're going to divide that sum by the sample size n. Okay? Now we can think of the mean as the balance point. The mean is the balance point of our data. So you could imagine having a box plot. Okay. So here's a box plot right here, and if we if each of these dots were a stone, okay, or a weight, you can imagine each one being some kind of weight, and imagine this piece across the bottom was like a plank, okay, like some kind of plank, and we're going to put this on a seesaw. Where would we put the little the tipping point, the fulcrum, so that the seesaw stays balanced? And we would put it right here. So this is the mean, the balance point, so that this scale of, imagine each dot is a stone, it's the balancing point here. And that is what the mean is. The mean is where all of these things would be in balance. Okay? Now the book says the mean is preferred when our data is symmetric. So this thing looks fairly symmetric, and it would say the mean is a good value to use to summarize symmetric data. Okay? The mean might be preferred when our data is symmetric. Okay. The mean can still be calculated for skewed data. Okay. Just because the data is skewed doesn't mean you can't calculate the mean. You can still calculate the mean. Okay. We can still calculate the mean for skewed data, okay, but it may not be as, quote, representative or typical when the data is skewed. Okay, but so you can imagine, because the mean is the balance point of our data, let's say you have something where you've got a bunch of values. So I'm going to just draw a bunch of dots over here. So pretty much, so if this were our seesaw, we would just say the mean, or if this was our entire data set, we would just put the mean somewhere like right here, okay? if that was our entire data set. But if we include a dot way out here, okay, suddenly, in order to keep this whole thing balanced, okay, rather than being in, or, you know, let's say I just put two things over here, suddenly, in order to keep this thing balanced, the mean gets, I don't know, pulled somewhere out here. Okay. All right, so you know, without those two dots, it might have made sense to say the mean was somewhere around here, okay? But now that those two dots are in play, suddenly, perhaps, I don't know, is this where the mean would be? I don't, you know, or actually, I don't know, maybe it needs to be out here, okay? So this is the mean to keep the thing balanced with these two dots out here. Okay? And so, so in this case, okay. So we want to, you know, in order to accommodate these two out here, you know, the mean suddenly gets pulled out here, and then, you know, is this a representative value? So, I mean, just to illustrate this, let's say we have six. There's a, maybe you're at a diner in a small town. Okay. And then and maybe there's 6 patrons there. And we ask each of them, how much money do you make, okay? And we get responses like this. Okay, so if we calculate the mean at this point, the mean is equal to 65,000. This is the mean income for these 6 people, okay? And it would make sense to say that that this is a typical amount of income for the people in the diner. Okay, let's say a very rich person walks in. So I don't know. Let's say Bill Gates walks in. I don't know how much money he makes, but let's say he makes $10 million a year. Okay? Huh? He makes what? Okay. Well, anyway, let's say somebody who has an income of $10 million per year walks into the diner. Okay. What is the mean income now? Okay. So the mean income now including the millionaire would be what? We would have to add up all of these numbers, and we would get 10,360,000 divided by 7. Okay, so if I add, or I'm sorry, not 10,360,000, it would be 10,300,000, let's see, 15, 20, 390,000. Okay, 10,390,000 divided by 7. Okay. And we would get $1,484,285. Something like that. Okay, unless I made a mistake, which I could have done. Okay, but we're going to get something in the vicinity of $1.5 million. Okay, now does that seem like it would be reasonable to say that the typical income in this diner is $1.5 million? No. Okay, and that's because here we have something that's very, very right skewed with one person making 10 million, and that's going to affect the mean. Okay, so the mean is very much affected by extreme values. Okay, so that is the mean. The other measure of center or central tendency is the median. Okay. Another way to summarize the center. Or the central values of a distribution of data. Center of a data set. Okay, so the mean is one way. The median is another way, and the median is the halfway point in our data. Okay. And so wherever the median is, you'll have half of the values will be smaller, will be less than or equal to the median. And half will be larger. Greater than or equal to the median, I'll say. Okay. Or another way to think about the median is, if you had some kind of histogram, wherever, so here's just another histogram. I know this is for a different problem, but it would be, if you had to paint this in so that half you use, where will you use exactly half of your paint, okay? And I don't know, it's a little tough, but I would judge maybe around right here we would have painted half, where to draw the split. So we have two sides that are the equal area. Okay. And so, it's a tough judgment call, if we're just eyeballing it, but perhaps maybe I don't know, does that look like they have approximately the same areas? Maybe not, something. Okay, that's my hope. Okay, so approximately the same area of green and blue. Okay, so that's where we would say the median is. Okay, and if it's symmetric, then the median and the mean will be the same. Okay, for symmetric data, the mean and the median will be almost equal to each other. The balance point will end up often being the halfway point. Okay. The mean and median will be equal or close to equal. Okay. The median is not affected by extreme values. Okay, so, you know, let's just go back to that diner. We have 60,000, 60,000, 65,000, 65, 70, and 70,000. Okay, so with just the 6 diners, our median would be right here. It would be the spot where we would split. So we have 6 people, 3 have lower, less than or equal to, and 3 have higher than or equal to. So we have 65,000, and then so you have 3 less than or equal to the median, and you have 3 that are greater than or equal to the median. Okay, so that is the diner with 6 people. Now I'm going to just copy this, and let's say again some rich person walks in making 10 million a year. Okay, at 10 million a year, we would have to draw the median so that this our median here is still 65,000. You have 3 that are less than or equal to the median, 3 that are greater than or equal to the median, and you have 1 that's actually equal to the median. The 1 is 65,000. Okay, so the median here is 65,000. So in this case, it was unaffected. In some cases, the median might be just affected by a tiny bit, but it's not going to be dramatically affected like the mean was, where the mean suddenly became, you know, $1.5 million or something like that. Okay, so how do we calculate the median? Okay, so to find the median, okay, number 1, always arrange from least to greatest, or arrange your values in order. Okay. Okay, and then count how many values you have. So if you have, you know, and then find the median by finding the spot. Where n over 2, or half of the values, okay, and then so there's kind of like 2 cases. So if you have an even number, an even n, even number of values, then the median is between the middle 2 values. Okay, you need to have n over 2 smaller or equal to, and n over 2 values greater, or okay, if you have an odd n, okay, then the median is equal to this middle value. Okay, and you still have half of the values smaller and half of the values greater. So you might have, so over here, you know, let's say I have 10, 12, 15, 18, 22, 29. Okay, 6 values. Okay, so with 6 values, so n is equal to 6. Okay, the median is equal to the average of 15 and 18. So 15 plus 18 over 2. This gives me 16.5. Okay, that's my median. And you've got three values over on this side, 3 smaller, and 3 greater. Okay, let's say I have 7 values, 8, 10, 15, 20, 25, 30, 32. Okay. Well, in this case, with 7 values, so n is equal to 7. So 7 over 2 is 3.5, but we were going to have 3 smaller, 1 median, and 3 greater. Okay, and so here the median is 20. And then you got 3 values that are greater, 3 values that are smaller. Is that okay? All right, so that is the mean and the median, and those summarize central tendency, or what we might call a typical value. Okay. We have to talk about this concept of spread or dispersion, okay? And this is actually a very key component to statistics, okay? Variation, also known as variation or spread or dispersion. Okay, and this is a key component in statistics. So when we talk about statistics, oftentimes we're trying to get an idea of how much variation naturally exists and how much of it is caused by something unusual. So when we want to make conclusions from our data about the population, there's a question of, could what we see just be a result of natural variation, or does the data indicate that something more interesting is going on? Okay, because when you look around the world, everyone is different, right? You have tall people, short people, you have just everyone is different. Whatever aspect about a person we're talking about, people are different, okay? Even if and so people are very different from each other, okay? Things that we might even expect to be pretty uniform, such as the chairs in this classroom, also exhibit a little bit of variation from one chair to another, okay? Except the amount of variation from one chair to another, there's just a tiny bit of variation, okay? So one might be a little bit more squeaky than another, or one might be just a tiny bit more comfortable or a tiny bit more soft or something than another. But in terms of the chairs, they exhibit a lot less variation, okay? Whereas with people, we expect a lot of variation, okay? If we think about pets, okay? Dogs exhibit a lot of variation in terms of size, okay? So when you go to the pet store and you want to buy a pet carrier, they're going to have pet carriers for small dogs, medium dogs, big dogs, and possibly even really big dogs, but they might have like crates or something like that, okay? But if you think about cats, okay, they're pretty much only going to have one size carrier for the cat, okay? Yes, cats, there are big cats and there are little cats, but as far as pets go, most of your cats are of a typical size, okay? Maybe you have a cat that's fat and overfed, but it's not going to be 10 times bigger than another cat, okay? Whereas with a dog, it's not that unusual to have two dogs where one dog is literally 10 times bigger than another dog, okay? Because you can have dogs that are 180 pounds, okay? And you can have dogs that are less than 10 pounds, okay? So dogs exhibit a wide amount of variation or a wide amount of spread, whereas cats, you know, the biggest house cat versus a small house cat, as long as they're adult house cats, maybe the big one is twice the size of the smaller cat, okay? But if you find a big dog and a small dog, the big dog could easily be 10 times bigger than the small dog, okay? So when we talk about variation and spread, this is what comes to mind, right? So, all right, so rather than just saying there's lots of variation or little variation, we can quantify this amount of spread, okay? So maybe to illustrate this, well, so maybe I'll just do some examples, okay, that we've already discussed. We'll say, you know, dogs have high variation or high spread, okay? You know, you can have, and then, you know, cats have some variation, but much less than dogs. Okay. Maybe another illustration. Okay. Let's say we have two families. Both families have 5 kids. Both families, and in both families, the average age, or the mean age, is 9 years. The average age of the kids, okay? So at this glance, it might seem like the families are quite similar, okay? But let's say we have family A, okay? And we have family B. Okay? So in family A, this will be John Adams. There, I don't know. Okay. Family Adams, we've got, we'll say the kids are 7, 8, 9, 10, and 11 years old. Okay? And in family B, the kids will be 1, 5, 9, 13, and 17. Okay? And so if we picture life in family A, or the Adams family, we'll, you can kind of picture what life is like there, and the kids are all very close to each other in age, okay? And so maybe, you know, you can imagine what life is like there. And over in the Baker family, the kids are very spread out in age, okay? And so, you know, you probably have a child still in diapers while the oldest one is driving and probably taking care of the younger ones and things like that. So you've got the picture of these families are very different, okay? So here we would say we have low spread or low variation, and over here we have high spread. Okay. And so just summarizing the number of kids and the typical age or the average age is not enough to really capture the full picture. And so we want to include the amount of spread. Okay, and so we can quantify this using the standard deviation. Okay, so the standard deviation and there's the statistical statistic, the variance. Okay, so the variance and the standard deviation quantifies the amount of spread. Okay, and so we can think of, I'm going to define the variance as equal to the quote-unquote average, and I have average in quotes here, average squared distance from the mean. Okay, and the standard deviation is just the square root of the variance. Okay, so let's take a look at the Baker family. Okay, and their ages were 1, 5, 9, 13, and 17. Okay, if we add these up and we calculate the mean, we would get, yeah, I can show you 1 plus 5 plus 9 plus 13 plus 17 is 45. Divide that by 5. We get the mean is equal to 9. Okay? So we've defined variance as the quote average squared distance from the mean. Okay? So let's ask, what is the distance of each point from the mean? Okay? How far is 1 away from the mean of 9? It's 8 units away. So I could just do 1 minus 9, and I would get negative 8. It's 8 units below. How far is 5 from 9? Yeah, 4 units below. What about 9? It's right at the mean. Okay, 13 is 4 units above the mean, and 17 is 8 units above the mean. Okay, so these are the distances from the mean. We can have the squared distance. And so when I do negative 8 squared, what do I get? 64, because a negative times itself will always, times a negative is a positive. Negative 4 squared is 16. 0 squared is 0. 4 squared is 16, and 8 squared is 64, okay? So these are the squared distances, okay? And so when I do, when I talk about the average, I have average in quotes, okay? Because normally to get the average, you would add them up. We have 5 numbers, so we would divide by 5. In this case, we would add them up, and we would divide by 1 less than 5, so we would divide by 4. Okay, so yeah, here I have averages, and we're going to say add up and divide by n minus 1. Okay, and you might ask, why do we do that? And the answer is, it's beyond the scope of this course. It's something called Bessel's correction. You can look it up on Wikipedia if you want. but it's probably too much for you to want to have to read through that article. Basically, you know, if we're trying to estimate the variance in the population, what we should be doing is calculating the distance from the mean of the population, but we're estimating the mean of the population based on the mean of the sample, and that's going to introduce bias into our calculations here. But anyway, don't worry about it. Just add them up, and we're going to divide by n minus 1 rather than n. So we would do 64 plus 16 plus 0 plus 16 plus 64. And then instead of dividing by 5, we would divide by n minus 1. So when I add these up, I think I get 160, but let me see, 64 plus 16 plus 0 plus 16 plus 64, 160 divided by 4, and 160 divided by 4 is 40, okay? So the variance is the average squared distance from the mean, the quote-unquote average, so my variance is equal to 40. The standard deviation is the square root of the variance, so my standard deviation is equal to, the standard deviation is equal to the square root of 40. And what's that? I'm going to do the square root of 40. I get 6.3245, or 6.3246. And that's my standard deviation.
How would you use variance, that number 40? What does that relate to? How is that useful?
It's just a number that quantifies the amount of spread that we have, okay? So it's perfectly legitimate to say the variance in the Baker family is 40. The units is a little funny. It's 40 square years, which I don't know what that means in real life, but it's okay, okay? We just have a funny unit, but it's a way to just quantify the amount of spread. We would say in the Baker family, as far as the ages of kids go, the variance that exists there is 40. For the other family, the variance that exists there is only 10 or something like that. And so we could compare the amount of spread in ages, okay? Or actually in the other one it would be 5, okay? Is that okay? So why don't you guys try this out? See if you can find the variance and standard deviation of ages for the Adams family. Find the variance and standard deviation of ages. Okay, so we have 7, 8, 9, 10, 11. Okay, so these are the ages. The mean is equal to 9, so you want to find distance from the mean, the squared distance, and then the quote-unquote average squared distance. And once you get the average squared distance, then find the standard deviation. Okay. If you're watching on YouTube, I'm going to pause the video here, and as soon as I unpause it, we'll be going over the answers. So I advise you to pause as well. Okay, so if we want to find the variance and standard deviation of the ages, we want to find the average squared distance from the mean. So we're going to just kind of subtract the mean off of each of these things, and we're going to get the distance from the mean, which we have is -2, -1, 0, 1, and 2. This is our distance from the mean, which means our squared distances from the mean will be 4, 1, 0. 1, and 4. And so the average of this will be, we add these up. And we're going to divide by n minus 1. So we're going to have 10 divided by 4. Our average squared distance from the mean is 2.5. This is my variance. So the variance is equal to 2.5. And my standard deviation is going to be the square root of 2.5. So I would just do square root of 2.5. And I get 1.5811. And that's my standard deviation. Okay? And so, one way to summarize kind of how the Baker family and the Adams family are different is we could say both families have a mean age of 9 for their 5 children. Both families have 5 children, and the mean age of the children is 9 for both families. But in the Adams family, the standard deviation of ages is 1.581, or the variance of ages is 2.5. And in the Baker family, the standard deviation is 6.324, or the standard variance is 40, okay? And that would tell us that in the Baker family, the ages are much more spread out, and in the Adams family, the ages are much more close together, okay? And when we saw the two data sets themselves, that was very clear to us. But there are many other cases where you just have a mix of numbers and it's not quite certain which data set has more spread than the other. And in this case, those cases, the formula for the standard deviation or the variance can quantify that amount of spread, okay? Is that good? I'll throw the formula for the standard deviation. So the standard deviation, the symbol is S, and the formula for it looks complicated, but it's not too bad. I mean, you don't have to memorize it. If you remember the standard deviation as the square root of the variance, and the variance being the, quote, average squared distance from the mean, I think it's quite clear what this is, right? So we see x minus x bar, this is distance from the mean. Okay, and if we square that, this becomes the squared distance from the mean. And then when we add those up and divide by n minus 1, that becomes the average squared distance. And then, and lastly, if we take the square root, then you get the standard deviation, this square root of the variance. Okay, so the formula is just a shorthand of all of these steps. You don't have to write them all out. It's just one way to kind of point out how we are calculating the standard deviation. Okay. If someone were to ask you, what is a standard deviation? What would you tell them?
Square root of variance.
Okay, well, that's not a very useful thing, right? If somebody asks you, what is a standard deviation, why would we bother calculating a standard deviation? Telling them that it's the square root of the variance is technically correct, but it's not a useful answer. Someone says, why do we have to learn what a standard deviation is? You would tell them,
The most common distance from the mean.
it's not I wouldn't say it's the most common distance from the mean. Or what's the point of calculating the standard deviation? Yeah.
The thing is that when you move it to the variance, you're squaring it, and so it's not the actual number that you're dealing with. So when you square it back,
Okay, maybe my question was too general. I was just kind of asking, like, what's the point, right? Like, why are we getting this? Okay? And so the standard deviation, if anything, okay, the standard deviation is a numeric summary that quantifies or assigns a number to the amount of spread that exists in our data, okay? Or is a, it's just as a way to quantify or basically assign a number, quantify the amount of spread that exists in our data. So earlier when we were talking about cats and dogs, okay? For cats, we would expect the standard deviation of weight to be fairly small. Okay, we expect most cats to be within a few pounds of each other, and so we would expect the standard deviation, which is just a way to quantify that, to be a small number. Whereas if we were talking about dogs, the standard deviation, we expect that number to be big. Okay, so it might be standard deviation for cats is like 3 pounds or something. Standard deviation for dogs might be 20 pounds, okay? Something like that. Where we are expecting the amount of variation or the amount of spread to be much larger for the dogs than for the cats, okay? And so the standard deviation is just a way to quantify the amount of spread that exists in our data. And the way we calculate that is we take the square root of the variance, and the variance can be thought of as the, quote, average square distance from the mean, right? Okay, the standard deviation is it's a useful tool because we can start to not just quantify the amount of spread, but we can say this point is unusual. Okay, so we can calculate distances from the mean in standard deviations, and this is called a Z-score. Okay, a Z-score is the distance from the mean in standard deviations. I think the air turned off and it suddenly feels really quiet, right? Okay, so the distance from the mean in standard deviations, okay? So let's say for adult women in the US, the mean height, or the average height, is, we'll say, 5'4", okay, or 64 inches. Okay, so we'll say this is the average height of women in the United States. Okay, let's say the standard deviation of heights, let's say is 3 inches, okay? Just so we have nice, even numbers. All right. So here's the question. Okay, what is the Z-score of a woman who is 70 inches tall? So how much higher than the mean is she? She is 6 inches taller than the mean. How much is that expressed in standard deviations? She is 2 standard deviations above the mean. Okay, so her Z-score is 2. So Z equals 2, okay? So she is 6 inches above the mean. Okay, we do 70 minus 64, that's equal to 6. Okay, her height is 70, the mean height is 64. she is 6 inches above the mean, okay? 6 divided by 3, okay, each standard deviation is 3 inches. Each S is 3. So she is 2 standard deviations above the mean. Does that make sense? Okay. What is the Z of a woman who is we'll say 59.5 inches tall? Anybody? Yeah.
Negative 1.5?
Negative 1.5, exactly, okay? So her Z-score is negative 1.5. So what we're doing is we're taking how far she is from the mean, 59.5 minus 64. So we see that she is 4.5 inches below the mean, but we want to express that in standard deviation, so we're going to take that distance and divide it by 3, because each standard deviation is 3. And this gives me negative 1.5. I just want to pause and make sure that this makes sense to you guys. We're trying to find the distance from the mean, but we're going to express that distance not in just the inches or however it's being measured, but we're expressing that distance in standard deviations. Okay, and so Z-scores are useful to us because just from a Z-score we can get a sense of whether or not a value is unusual. Okay, can I flip to the next page here? All right, so Z-scores give us a sense of how unusual a data point is. Okay, so for a unimodal and symmetric distribution, okay, we expect nearly over 2/3. So we expect 68%. So just, over 2/3 of the data to have Z-scores between -1 and 1, okay? Or another way of saying that is that 68% of the data is within 1 standard deviation, 1s, of the mean. Okay, so if we were talking about women's heights, so we said mean height for women is equal to 64 inches, and the standard deviation is equal to 3 inches. So we expect about 68, about 2/3 of the women to be between 61 inches and 67 inches tall, which is 5'1" and 5'7". So we're ballparking it, and these are just kind of numbers that are rounded off for convenience sake, but about 2/3 of women are between the heights of 5'1" and 5'7". Okay? And perhaps that matches your experience of encountering other people. Okay? We would say about 95% of data have Z between -2 and +2, okay? Or 95% is within 2 standard deviations of the mean. Okay, so about 95% of women are between 58 inches, so that's 4'10", and 70 inches, 5'10". Okay, that's what for women, about 95% are between 4'10" and 5'10". Okay, and then nearly all, so 99.7% of the data have Z's between -3 and +3. Okay. So what does this mean? This means what's going on? Okay. So this means if a z-score is more than 2 units away from 0, so if z is greater than 2 or less than -2, it's unusual. Okay, so z greater than 2 or less than -2 is unusual. And z greater than 3 or z less than -3 is highly unusual. Okay, because this set of numbers here, this is called these are called the empirical rule. Sorry, it's known as the empirical rule, and that just means this is what we're expecting when we look at our data, that about 95% will have z's between -2 and 2, and 99.7, so almost all will have z's between -3 and 3. Okay, so z's greater than 2 or less than -2 is unusual, and z's greater than 3 or less than -3 would be considered highly unusual. And so we can compare apples to oranges in this case, and we can just calculate z-scores. So we can compare, you know, quote, apples to oranges through z-scores. And all we have to do is we would calculate the z for each value, okay? So, you know, what is more unusual? Maybe a 10-pound Chihuahua or a 200-pound Great Dane? Okay. And I think, let me ask Google, average weight of a Chihuahua.
Chihuahua has a weight of 3.3 to 6.6
Yeah,
pounds.
so, okay. So what's more unusual, 10-pound Chihuahua or a 200-pound Great Dane? Okay, well, for the Chihuahuas, the mean weight is something around 4.6 pounds. Okay, and the standard deviation is maybe like 1 pound. Okay, we'll ask for Great Danes. Average weight of a Great Dane.
The weight of the Great Dane breed is typically between 99 pounds and 130 pounds for females, and between 120 pounds and 200 pounds for males.
Okay, and so for Great Danes, at least for male Great Danes, the mean weight is around 160 pounds, and the standard deviation looks to be about 20 pounds. Okay, and so for the 10-pound Chihuahua, its Z-score would be 10 minus 4.6 divided by 1. This thing has a Z-score of 5.4. Okay, and over here for the 200-pound Great Dane, its Z-score is 200 minus 160 divided by 20. It has a Z-score of 2. Okay, and so the 10-pound Chihuahua is highly unusual because it's 5.4 standard deviations away from the mean. Okay, and that's really, really crazy. Okay, whereas for the Great Dane, it's 2 standard deviations of the away from the mean, which is unusual, but it's not on the magnitude of 5. Okay, so the Chihuahua that weighs 10 pounds is much more unusual. Than the 200-pound Great Dane. Okay. So that's what we have here. So you can compare things. All right. We run out of time. We have to talk about quartiles and the IQR. IQR and then box plots. Okay. So we've already talked about the median. Okay. So the quartiles. Let me define Q1, which is our first quartile. This is the 25th percentile. What does it mean to be in the 25th percentile? This means 25% of the data is less than or equal to this value. Okay. Q3 is the third quartile. That is the 75th percentile. So 75% of the data less than or equal to this value. Q2 would be what? this is the 50th percentile. We can call it the second quartile, but we'll call it the 50th percentile. And what's that? Okay, we can say 50% of the data is less than or equal to this value. And what's another thing we call that? The median. Q2 is the median, right? The halfway spot, where half of the data, or 50% of the data, is less than or equal to this value. Okay? So the IQR is the interquartile range and it is the distance between Q3 and Q1. Okay? So to find the quartiles, all you do is you take your list of numbers, find the quartiles, find the median, and once you find the median, that's going to split your list in half. And effectively, you're going to just take each of those half lists and find the median of the half list to get the quartiles. I'm going to flip to the next page. So to find the quartiles, first find the median. Okay, then use the median to split your list in half. And then find the quote median of each half list. Okay, and those would be the quartiles. So let's say we have 20, 22, 24, 26, 30, 31, 37, 40, 42, 1, 2, 3, 4, 5, 6, 7, 8, 9, 44, 50, and 58. Okay? So here I have 12 numbers. Okay? So first we're going to find the median. Okay, so we're going to find the spot where 6 values are smaller and 6 are greater. So this is the median. The median will be 31 plus 37 over 2. I get my median to be 34. And so now I've got one list that's smaller and one list of 6 that's greater. Okay? And so Q1 is going to be kind of the median. Okay, so the quote median of these 6 numbers, and that's going to be Q1. So Q1 will be 24 plus 26 divided by 2. So Q1 is equal to 25. And over here I'm going to find the median of these 6 numbers, and this is Q3. So that would be 42 plus 44 divided by 2. And I would get 43. So Q1 is 25, Q3 is 43. My IQR is Q3 minus Q1, 43 minus 25. I have an IQR of 18. Okay, are there any questions on this? Okay, if you have an odd number, or there's a question?
Yeah, just a clarify. So Q1 is the median of those 6 numbers?
Correct.
Yeah.
Yeah. If you have an odd number, if your original list has an odd number, that means your median will be one of those values, right? Don't include that value in the half lists that get calculated in the future, okay? So, you know, for if you have an odd n, do not include the median in each of the half lists. Okay. All right, and in my last 7 minutes here, we'll talk about the box plot, okay? So we've talked a bit about getting Q1 and Q3. And so there's one more graphic display, and this is called the box plot. Okay? And a box plot will look something like this. There's a rectangular box, maybe with a line in it, maybe some lines coming off of it. Okay? And then perhaps some dots. Okay, this is the box. These things are called whiskers. Okay, so I'm going to label these. So the box is defined by 3 values. Q1, or the 3 lines on the box, are Q1, the median, and Q3. Okay. This thing is called a whisker. This is also a whisker. And there's an invisible line called lower fence and upper fence. And these are data values that are outliers. Okay. What does it mean to be Q1? Q1 is the 25th percentile. So 25% of the data is smaller than Q1. How much of the data is between the median and Q1? 25%. How much is between the median and Q3? 25%. And how much is greater than Q3? 25%, okay? How much is in between Q1 and Q3? 50%. The middle 50% of the data is contained between the boundaries of the box, okay? So these are some good things to keep in mind, okay? So the middle 50% of the data is between Q1 and Q3, or within the box. Okay. The fences are invisible, but they're invisible boundaries that separate outliers from the rest of the data. Okay. Okay, and so box plots are useful when you're comparing one box plot for one data set to another data set and their box plot, okay? Because by looking at the width of the box, what is the width of the box? The width of the box is the IQR. The IQR is Q3 minus Q1, which is effectively the width of the box, okay? Okay, so you can look at the width of the box and you can get a sense of how much spread is in one data set versus another data set. You can look at the location of the median, which is just that bar that's in the middle of the box, and get a sense of where the middle point is. You also get a sense of if there are any outliers, okay? So looking at this, would you say our data is right skewed, left skewed, or symmetric?
Left.
I would say it's right skewed, okay? Because looking at where the median is for where typical is, we see we have some outliers to the right, but if we go in the other direction, do we have any outliers to the left? No. The lowest point to the left is down here, whereas we have some values that are much higher. Okay, and so this would be right skewed. Okay, so you would just look at, I know the left side of the box is bigger than the right side of the box, but that doesn't make it left skewed. You're looking at kind of the extreme values. So whether it's skewed or not depends on if there are extreme values much higher or extreme values much lower, or if there's about the same number of extreme values above and below. Okay. So, so that's a box plot. Okay, and that takes us to 10 o'clock, so we'll end here. We'll see you guys next week.